exist in the subsurface, and hopefully to also constrain the possible magnitudes of stresses which could exist at different depths. And we're interested in that because it's obviously very important to understanding the ongoing and past plate tectonics of the region, how that plays into the inactive fault systems of the mountain belt. There's also significant isostatic rebound in the region, which can obviously create some interesting states of stress in the subsurface. There's some concern that those states of stress could also activate those existing mountain belt fault systems, which could pose an earthquake risk as well. So in a moment, I'm going to talk about the first step to our method of investigating those stresses. But first, I want to remind everybody that we can model these stresses as a principal stress tensor with a vertical stress and two horizontal stresses. Our project seeks mostly to characterize this greatest horizontal stress, shown here as SH. And you can see there's been a lot of work in recent years and throughout Europe trying to characterize the direction and magnitudes of these stresses in the crust. So our project, again, is up here in Western Sweden. And by adding more information to this map, we can have a better idea of what the crust is doing there and in the wider region. Okay, so how do we determine these stresses? Well, when we drill a borehole into the surface, we can create some pretty extreme stress concentrations. So as you can see here in these red areas, this is where we have breakouts. We have a concentration of compressive stresses, and we also have parallel to the greatest horizontal stress. We have these regions of increased tensile stress, which can also create fractures. And what this causes is it causes these hemispherical regions of fracture and failure, dog-earing out at either side of the borehole. And we can see in 3 dimensions that the orientation of those breakout areas changes relative to the orientation of that largest horizontal stress. So one way that we're able to map these breakouts is by using a ultrasonic televiewer. It's like that, and we can drop it down the borehole, and what we're looking at here is kind of like an opened up view of the entire circumference of the borehole. And it operates much like a modern medical instrument. We're just sending ultrasonic pulses into the rock and measuring their reflections, and we can see that we have these paired regions where we have very low reflected amplitude of signals and increased transit time in those areas. And that's because when we bounce a ultrasonic wave like out through one of these areas of failure, the wave is often reflected out away from the borehole rather than back in, where it can be measured by the televiewer. Okay, so hopefully now have a better idea of how we determine the directions of stresses within the crust. I'm now going to pass it over to my colleague Angee, and she can describe the rest of our method, how we determine rock strength, and correlate that with P and S wave velocities in order to constrain the magnitudes of stresses throughout the borehole.
Okay, so our first step is to calculate physical properties such as density and porosity through helium trigonometry. And then for permeability and geochemistry, we obtain this data from our coworker Simona, who's been working in thickness sections in Germany. Our second step is just putting our samples into a pressure vessel and trying to get some velocities for S and P wave, so we can calculate shear and bulk modulus, Poisson ratio, and BP-VS ratio. And our final step is to do the uniaxial compressive strain test. We just wire some strain gauges to the samples and put it in a press and squeeze it until it fails. Okay, so you can here see the arrangement of the pressure vessel. We just put the sample in between these two end caps transducers, and we just put it under pressure up to 200 MPa, and we just take the time for the way to transit through the sample. So these are one of the results. You can see the waveforms and you can see how it's pressure dependent. So when you're going up in pressure, the time reduces, and you can see we have just this peaking system that is very simple. And this is one of our organic rich shales. And you can see the pressure dependence and the hysteresis that Doug was talking about. And these are the results for P and S waves. These are the equations that we are using to calculate shear, P wave, and bulk modulus. That data help us to understand the elastic properties and rigidity of the samples, and we use that to understand the strength in the borehole. So we are actually not doing the UCS test. That's our future step, but there's a video you can see for an example. Videos on so our future work, our next step is to start with the UCS test. We'll probably start with this the next month. And we want to correlate the strength with the velocity data that we're getting right now. And we want to determine and constrain the stress directions and magnitudes. And we want to correlate the strength with the velocity so we can extrapolate all the information to the borehole model and have an idea of all of the strengths in the borehole.
Okay. Thank you. I think we have time for questions now, correct?
Yeah.
Okay.
Couple of questions.